All right, everybody, welcome to the sixth, screencast of Chapter 2. Now we're going to take things out of the single-dimensional world and into the two-dimensional world. And let me say a little bit about that, that nomenclature, single-dimensional, two-dimensional. What we're talking about when we say that, we're talking about the number of issue dimensions there are. Of course, we saw in the single-dimensional model, there is a second implied utility dimension that we kind of get rid of. We don't get rid of it really. We don't have to draw it anymore once we assume single-peaked and symmetric utility. So when we say a single-dimensional spatial voting model, we mean one issue dimension. And the same thing is going to hold here with two-dimensional models. There's going to be a utility dimension. But then we're going to make our assumption about single-peaked and symmetric utility, and we're going to be right back down to a two-dimensional graph of the two issue dimensions. But that third utility dimension is there also. For those of you who have had intermediate microeconomics, the same thing is true, of course, in the indifference curve budget constraint model that we use. We have usually two goods, X and Y, or X1 and X2, but there's that implicit utility dimension that the utility functions have. It's very similar here in the two-dimensional models. So for those of you that have had that, hopefully some of this way of thinking will match up. But I'm not assuming that anyone has had intermediate micro for these slides. We're going to build everything up step by step. So let's start doing it. So just to remind you, we had this single-dimensional model. This is basically just some pictures of what I just said. And here are three voters, voter 1, voter 2, voter 3, and they have these utility functions. All of these voters have single-peaked, but not symmetric utility, all right? But if we have one voter here who does have single-peaked and symmetric preferences, this voter 2, then all we really need to know in terms of how much does he or she like something is how far is it from their ideal point. The ideal point, again, is the point in the issue space that maximizes their utility function. So if we assume single-peaked and symmetric preferences, then all we need is the utility dimension. This agent here, voter 2, is indifferent between alternative 1 and alternative 2. Those are his indifference points, all right? Everything in between the indifference points is his preferred 2 set. He prefers those things strictly to either alternative 1 or alternative 2. And then everything outside of that, he strictly likes less than alternative 1 and alternative 2. We're going to have something very similar showing up here in our two-issue dimension model. So what we do is we can get rid of the utility dimension. We don't need to explicitly draw it. And what we have to worry about then, is distance on the number line here. So it's going to be very similar. But now we're going to go two-dimensional. All right. So the way we're going to start is I am going to include that utility dimension. All right. So that we have a picture of what it looks like in our heads, so that then we can drop it. And we'll just basically know everything is distance. It's the same metric in terms of what gives me higher utility. It's the thing that is closer to my ideal point. That's going to be the same, all right? But first, let's get a picture of what that looks like in our head. So first, I'm going to put the dimension 1 and dimension 2 here kind of on the floor, as it were. So if we were in a room, I would be walking around and saying this bottom corner where the floor meets the wall is dimension 1 axis, and this from the same corner going out along the other edge where the wall meets the floor is dimension 2. And then, of course, utility is where the two walls meet. And that's how I would try to help us get a picture of what that looks like. And then, of course, a utility function in that space would map different combinations of dimension 1 and dimension 2 and tell us how much utility the agent gets for, say, this point right here. And it could look something like this, right? In the natural sciences, they have functions that map 2 dimensions onto a third dimension like this that are all sorts of crazy types of functions. We're not going to have anything that complicated. So you, oh, it's coming back. You might think, oh, well, we would have something like this. Even this is more complicated than we're going to get with our utility functions, okay? This one has a single peak here. The point right here in the middle maximizes their utility, but it's not single peaked, right? Because it scoops back up. There's this ring of combinations of alternatives that give them higher utility than these down here in this valley. And I've just put social and economic as a way of thinking about what would these two different dimensions be. In many cases, we think about policy, at least in the US, in terms of economic and social policy. And in fact, if you're familiar with the DW nominate scores that are used in, extensively in political science, Keith Poole and Howard Rosenthal's invention of measuring and trying to estimate ideal points for members of Congress, they roughly say their first dimension is economic, and the second dimension, it varies over time, but we could just roughly, because we're doing a theoretical model here, just call it social issues, right? So economic issues and social issues, and then we have utility. But I'm just using that to give us a little more specificity. We can really be abstract, just like we were a lot of times with the single dimensional model, and just saying as long as everyone agrees that this goes left to right and there's one dimension, then we don't have to be precise about what that dimension is. But I like to put a little bit of texture on this at first until we get the hang of dealing with these two models. So what are our utility functions going to look like? Well, our utility functions are still going to be fairly simple. We're not going to have mountain ranges or surfaces like that, volcano surrounded by a donut or something like that. We're going to be assuming that people have single peaked and symmetric preferences. So they're going to have one point in the space that maximizes their utility, and then as you move away from that point, their utility function is going to slope downward, all right, as you move away from it. And we're also going to assume symmetric preferences. Symmetric preferences are a lot more important to some of the graphs we're going to have than they were in the single dimensional models. But as it turns out, none of the results require symmetric preferences. But again, it's going to make things mathematically a lot more tractable for us if we assume single peaked and symmetric preferences. What's going to matter is going to be Cartesian distance on that XY or economic social axes. And we're going to be able to get rid of the utility. But what might those utility functions look like? Well, I've got one more version of the single peaked and symmetric. Again, I'm going to show you one particular version. It's sort of the analog of this one for the utility functions. But because all that matters is distance, a voter prefers something closer to their ideal point. The shape of these for us, anyways, in more complicated models, these shapes certainly do matter. But for us, all that's going to matter is distance, right? Because as we move away from this voter's ideal, his utility is falling, and it's falling the same, going the same distance in the other direction. So what does it look like for us in two dimensions? Here I've got Jack. Jack has an ideal point here on the social economic plane, all right? So instead of it being a line, it's now a plane. So you can think of this as having Cartesian coordinates. You know, there's an X value and a Y value for this spot that is Jack's ideal point. That is his ideal set of economic and social policy, all right? We could also think of this in terms of, say, transportation spending, and we could think of automobile spending and all other transportation spending. And Jack has this ideal point in that space, which is his ideal combination of spending for transportation spending. So what would Jack's utility function possibly look like? Well, it's going to be single peaked and symmetric. So this is one version of that, this kind of parabolic almost utility function. And so here is Jack's ideal point, and you notice it is the one that maximizes his utility, all right? So that point maximizes utility. If I move away from Jack's ideal point, I'm going to be going down this surface. Now, ideally, one day I'll have a hologram machine and I'll be able to walk around and have a 3D thing and show you how this is a 3D surface. And as Jack walks in this direction, he's going downhill. But hopefully this is good enough and you can picture what it is that I'm talking about here. It could also be a sharper pointy cone, more like what we used in the single dimensional model. And this was the best version of that I could come up with here in keynote. But what really matters is that there's a global maximum, and as you move away from it, you would be going, let's say Jack was going this way on the economic social plane, moving this way, or a policy was moving that direction, it would be going down the cone in terms of the amount of utility that those policies as we move away from Jack's ideal. So it's very similar to what we saw when we had the single-dimensional model with a second utility dimension. Here we're going to have a two-dimensional model with a third utility dimension. So the further an alternative is from the voter's ideal point, the lower that alternative is on their utility mountain. All right. So as we move away from their ideal, they like those alternatives less and less. And we're going to just use Cartesian distance, right? Something way out here, Jack likes less than something closer to his ideal closer. So what are these lines here? Well, these lines are, if you know three-dimensional mathematics, if you remember from algebra and things like that, these are what are called level curves. They show all of the points in the space that give Jack the same utility. So here I've plotted an alternative y. All right, so Jack likes y less than his ideal point. It is further away from his ideal point than his ideal point. And it's further away than, let's say I put something here, a z or something. He would like z more than y, but y is out here. So what the level curve is it's the set of all points that Jack likes just as much as y. So it's the set of all points down here that would map up to the utility function at the very same height, which is u2 here. It looks a little weird because u2 is here, and it looks like this should be u1, but it's not. We're looking at it from a strange perspective here. So this is utility level 2. So all the dots, if we took this and basically squished this cone down to the ground, we would have these concentric circles. All the dots on that circle projected down to this plane would give Jack the same utility as y. All right, we call these in social science indifference curves. We don't really call them level curves, or sometimes they're called level sets. They have a particular meaning for us. They're indifference curves. It's the set of all points that Jack is indifferent to, and an indifference curve is based on a particular alternative. So there's a indifference curve for y, and then there's another indifference curve for, say, that z I was talking about, all right? Oops, that z I was talking about. It would be a circle down here. Now, it looks like it's an oval, and that's because we're looking at this from a 3D perspective. But you'll see, once we get rid of this utility dimension, we're going to be dealing with circles on a flat plane, all right? And we won't have to do this kind of skewed perspective, all right? So an indifference curve, what is it? It's given an alternative y. The indifference curve of y is the set of all alternatives that give the voter the same level of utility. That is, they are indifferent between all of those alternatives. All the alternatives on the indifference curve give them the same utility, therefore they're indifferent across those. If they were asked to vote between two things on their indifference curve, we don't know what they would do. We saw something similar in the single-dimensional model, right? We said if there was an alternative and they had an indifference point symmetric moving across their ideal point, we don't know which one they would vote for. But if you move inside of those indifference points, you're in their preferred to set. It's going to be very similar here. Inside of an indifference curve is going to be their preferred to set, all right? So let's, so that's the next slide here. The preferred to set of an alternative y is the set of all alternatives inside of the indifference curve. That also can be said, it's the set of all alternatives that are closer to the voter's ideal point than is y. And that's closer using Cartesian distance, which is regular old distance. There are other measures of distance. Those of you who've had that kind of mathematics or having flashbacks to Algebra 2, and sometimes you've dealt with those different measures, this is just plain old Cartesian distance. The distance between 2 points on a two-dimensional surface is that, it's that formula, all right? And so another way to say what is the preferred to set, it's the set of all alternatives that give the voter more utility than y. These are equivalent definitions, okay? So indifference curves are sort of like topographical maps, all right? A topographical map shows you all of the areas that have the same height, right? This is a topographical map of San Francisco. All right, so there's this really hilly area in San Francisco, and if you've, gosh, I'm forgetting already where everything is, but if you've ever taken the cable cars, you kind of go over the top of some of these hills. It's a really hilly area in certain places, and then other places it's not so much. Actually, I think you're probably down here, if I recall correctly. Gosh, I haven't been gone that long, but I can't remember all of the geography as well. But the indifference curves are a topographical map of the utility function, but it's much simpler than a topographical map of, say, a mountain or of San Francisco. It's this sort of simple shape. So the topographical lines, the indifference curves, the level sets, the level curves are going to be circles because we are assuming single-peaked and symmetric utility. So what does that mean? All that I care about really is how far is y from Jack's ideal point. That tells me what his level of utility is, and it tells me all the other points that he prefers the same amount. It tells me anything closer is in his preferred to set. Anything on that circle he is indifferent to with respect to y. So that we can get rid of the utility axis and we can do everything just on the two-dimensional plane. Now, of course, we don't want to draw a two-dimensional graph this way. We want to flip it up and draw it the way we're used to doing that. So here is what that would look like. Here's Jack. Jack has an ideal point in the two-dimensional space, and then there is an alternative y. What we care about is how far is y from x. All right? And then the next thing we're going to care about is what is the set of all things that are the same. Oh, I can't draw it. You'll be glad I did it with the computer. The set of all things that Jack is indifferent to with respect to y. And that what matters, again, is for utility is distance from the voter's ideal point. So these two graphs are equivalent. It's just over here, I've gotten rid of the utility dimension and flipped it around so we have a nice horizontal axis and a nice vertical axis, and we have Jack's ideal point, and we have this y here. And we can even add in the indifference curves. Here is the indifference curve for y. On the indifference curve u2, we basically just squished down this shape, this utility function, or another way to think about it is we're looking at it from directly above. Right? We are up here in the sky looking straight down onto this two-dimensional plane, and someone has labeled a couple of the indifference curves for us. Now, one thing to note is there's an infinity of these indifference curves. Every spot in the space has a level of utility and therefore has an indifference curve. So here we're just drawing a few of them. Just like on a topographical map, we only draw a few of the topographical lines. We couldn't draw for every point on the land where are all the other points on the land that have the same height, right? It would be a big, just a blob, right? Because there's an infinity of such points. Same thing here. We're just drawing a few of the different levels of utility here. But the one we're really going to care about is this level of utility. The level of utility for an alternative y, because we're going to want to know what would Jack vote for over y, and when would he vote for y against another proposal. And if that proposal is outside of his indifference curve, he likes it less than y, so he would vote against it. All right. So as I just said, there's an infinity of these indifference curve. I've just drawn 3 of them. All right. So let me bring in an example that we're going to work with through pretty much the rest of the chapter. We're going to have Ted, Barney, and Marshall, the How I Met Your Mother crew. We're going to bring Robin and Lily in later on. But these 3 have ideal points in the two-dimensional space. This is the point in the space that maximizes Ted's utility. As alternatives get further and further away from Ted's ideal, he likes them less and less because he's going downhill in terms of his utility function, which would now with this arrangement, the utility is basically coming out of the screen at you, the utility dimension. We're looking straight down on there. And so Ted has a set of indifference curves. Here I've drawn 1, 2, 3, 4 hypothetical indifference curves for Ted. Marshall may have indifference curves that look something like this, and Barney has indifference curves that look like this. They all have their single-peaked and symmetric utility functions, so they all have circular indifference curves, all right? Again, it's not going to really matter what one person's utility mountain looks like compared to another person's. All that's going to matter is comparing alternatives with a single person's utility function, all right? So it doesn't really matter if they all look very similar or if they look different. What matters is they're single-peaked and symmetric, and each voter likes things closer to their ideal than further away. Now, in some more sophisticated models, some of the ones that I use in my research, it does matter what kind of the shape of these things look like. But for now, we're just going to use these circular indifference curves. All right, and we could even throw all of them on there at once if we wanted to. Now, we're not going to need to do that ever in this class. There's no reason. It just kind of looks kind of cool. But what we're basically going to need to do is to say for a given alternative in the space, what is Marshall's indifference curve for that alternative? What is Ted's indifference curve for that alternative? And what is Barney's indifference curve for that alternative? So we're not going to draw families of indifference curve for each voter. We're going to draw one indifference curve for each voter going through a particular alternative in the space, okay? So we usually want to know only how they feel about 1 or 2 or 3 alternatives at a time. And we usually only draw indifference curves for one of the alternatives, all right? And you'll see what I mean when we get to that stuff later on. So that's the end of the intro here. Intro to two-dimensional spatial models. We're going to move on and start using these things in just a second.